Greetings everyone. I believe you're all well. Welcome to my YouTube channel for Kangaroo Medicine Science Academy. Tonight, guys, I want to take you through the photoelectric effect, which is Physical Science Paper 1 topic. Right, I believe, ladies and gentlemen, you'll enjoy the session for photoelectric effect. This is one of the easiest topics in Physical Science Paper 1. So remember, practice makes perfect. You see here, there's my YouTube channel. I strongly recommend that you go through it. Then you'll be able to have access to all the videos that I just posted. And kindly don't forget to like, subscribe, and hit the bell button for future video notification. Right, without wasting time, ladies and gentlemen, let's now start with photoelectric effect. Right, under photoelectric effect, first of all, we need to be able to describe what is actually photoelectric effect. I'll just go through it so that I can be able to do another summary of this. Right, in terms of photoelectric effect is the process whereby electrons are ejected from a metal surface when a light of a suitable frequency is incident onto that surface or is shined onto the surface of that metal. So this is called the photoelectric effect. And again, we must be able to state the significance of the photoelectric effects. Then again, you must be able to describe or to define what is a threshold frequency. We call it a threshold frequency or a cutoff frequency. So in other book, they call it a cutoff frequency. So we call it a threshold frequency or a cutoff frequency. So it means the word cutoff or threshold will be used interchangeably. So cutoff frequency is represented by symbol F0, which is the minimum frequency of light needed to emit electrons from a certain metal surface. That minimum frequency of light that is actually needed to emit or to eject electrons from a metal surface is called the cutoff frequency or the threshold frequency. We also have what you call the cutoff wavelength or the threshold wavelength. So you need to be able to differentiate that. But in terms of the cutoff wavelength is the minimum wavelength of light that is needed to emit electrons from the metal surface. So the only difference is that when we're talking about cutoff wavelength, we use the word wavelength instead of frequency. But it's also denoted by wavelength. We know it's lambda, but once we use the symbol lambda not, we know this represents threshold wavelength. We call it a threshold wavelength, threshold or cutoff wavelength. So you need to be able to understand that. So the cutoff frequency, as I said, is the minimum frequency of light that is needed to emit electrons from a metal surface. We'll be talking about this. And again, we'll be talking about a work function, which is represented by W0. Work function is the minimum energy that an electron in the metal needs to be emitted from the metal surface, or the minimum energy that is needed that an electron in the metal needs to emit electrons onto the metal from the metal surface. So the minimum amount of energy that is needed to eject electrons from the metal surface is called the work function. So it's very important for you to know what do you mean by a work function. It's very important. And again, we're going to talk about what you call we perform calculation using photoelectric effect. We'll talk about this and also talk about the effect of intensity and the frequency on the photoelectric effect. And what do you mean by intensity? Intensity has to do with brightness, has to do with the brightness of light. Right? How does the brightness of light has impact towards the photoelectric effect. We'll talk about that, ladies and gentlemen. Right, without wasting time, we are also going to talk about the difference between the emission and the absorption spectrum. So this is very, very important when we talk about in terms of electromagnetic radiation. So we'll actually talk about that. Right, without wasting time, ladies and gentlemen, let's now deep dive into photoelectric effect. This was just the basic. Remember, photoelectric effect, as I said, is the process whereby electrons are ejected from the metal surface when light of a suitable frequency is incident on that metal or shine onto that metal. So without wasting time, let me go deep and explain the key aspects of photoelectric effect. This is one of the easiest, guys. I believe you'll enjoy this session. So let me take you through step by step of the photoelectric effect. Right. Okay, let's now move on to, okay, let me just, I just want to find a place where I can do the summary. Yes, let me hear this. Right, let's say we have a light, consider a light. Okay, just use, consider we have a light. And this light has its own frequency of light. Let's consider this light with its own frequency. Let's just use symbol F. So it means now you need to be able to understand the symbol that we're going to be talking about. If I talk about F naught, you must be able to know this. It's a frequency, but we call it a threshold frequency. It's a threshold frequency. It's not of light, but if we use symbol F without the naught there, it is called frequency of light. So right, consider here we have a light, and this light has its own frequency. Then obvious, if we have a light and this light has its own frequency, then now we assume that, okay, this light, I mean to say, has to shine onto a metal. So let's just assume we have a metal here. This is the metal. Maybe this metal is made of sodium or potassium. It depends with the like the type of metal that we're actually talking about. Right now, obvious, if this is our metal surface, this is the surface of the metal. Is the metal, maybe it's made of sodium or any other metal. Then obvious, if we shine this light onto this metal, we shine the light onto the metal. So what will happen? If we shine this light onto the metal, there's a possibility that the metal can release electron. Not always that the metal will release electron when light shine onto the metal. Right, if we go back to the definition, like what I said the photoelectric effect, it says, photoelectric effect is the process whereby electrons are ejected onto the metal surface. This is our electron, assuming that they're ejected. So a process whereby electrons are actually ejected from the metal surface when light of a suitable frequency shine onto that metal. That is called photoelectric effect. Right. So what does this mean? It means that when light of a suitable frequency shine onto the metal, then the metal start to release electron or start to eject electron. Then this process is called photoelectric effect. Now, the question is one. Does it mean that if we just use any light and we shine it onto the metal will keep on releasing electrons? The question is no. Right. What causes the light not to release electrons onto the metal surface? Number one, the type of metal. Type of metal has an impact towards the electron ejection. Now, why am I saying the type of metal? If we use, let's say we are comparing sodium and let's say potassium or magnesium, it depends. Sodium and magnesium are different metals. So what does it mean? It means the type of the metal has an impact towards the electron ejection. So now, it means that if we were to talk about the metal, this metal, for the electrons to be ejected on this metal must have its own threshold frequency. It requires what you call a threshold frequency or the cutoff frequency, which is actually denoted by F naught. What is this cutoff frequency? The cutoff frequency is the minimum amount of frequency that is needed to eject electrons from the metal surface. So it means this cutoff frequency does not depend on light, but depends on the metal surface, the metal. So what does this mean? Different metal have different cutoff frequency or threshold frequency. So now, what does this mean, guys? It means that when light of a suitable frequency shine onto the metal surface, it means that the light that is shining onto the metal surface, it comes with its own energy. It comes with its own energy when it shines onto the metal surface. And this energy that is needed from the light is called the energy of photon. Denoted by E. So it means the energy of photon is the energy that is supplied by the light, not by the metal, but the light. So it means that when light shine onto the metal, it means this line comes with its own packet of energy, which is actually regarded as quanta. Right, or photons. So this energy of photon, it's actually the energy that is depending on the frequency of light, not onto the metal. So it means that different light will have different energy of photon. For example, if we compare a red light and a blue light, these will not have the same energy. Why? They have different frequency. Obviously, they will have different energy of photon. I want you to understand me very well. So which means that, ladies and gentlemen, when you are dealing with light, you need to be able to calculate the energy of photon of that light. So which means that when you are calculating the energy of photon of light on light, you use the formula. We use the formula E equals to HF. Remember I said once you see the F without the naught, you are referring, you actually know that we're talking about the energy of the frequency of light. So it means we are dealing with frequency of light, which is measured in hertz. Then how about the A? The A is called, the H is called the Planck's constant. Planck's constant, which we'll talk about, which is the same as 6.63 times 10 to the power negative 34. Now, I want you guys to listen to me very well here. However, this energy of light, or this light, when it's shining onto the metal surface, it comes with its own speed. So which means it comes with what we call the speed of light. Which speed of light depends on the frequency of that light and the wavelength. I think you recall when we spoke about the relationship between frequency of light and wavelength under Doppler's effect, where we said the longer the wavelength, the lower the frequency. Same applies here. So there is a formula of calculating the speed of light here, which says speed instead of v, speed is equals to force multiplied by lambda, whereby this c is actually the speed of light in a vacuum, which we assume it's, depending on the question, is 3 times 10 to the power 8 meters per second. So which means that if we do not want to calculate the energy of photon by using Planck's constant and frequency, we can still calculate the energy of photon by using the wavelength. How to do that? From this formula of C equals to F times lambda, we can divide both sides by frequency, by the lambda, and by the lambda, which is the wavelength, which means frequency equals to C over lambda. So what does it mean? It means if we do not want to calculate the energy of photon by using HF, we can still calculate the energy of photon where there is F, we substitute by C over lambda. It means this is HC over lambda. So it means when we have a wavelength, we can calculate the energy of photon when we use this formula, or we calculate the energy of photon to use when we know the frequency of the light. So these are the two formulas that we can use to calculate the energy of photon, onto the light, not onto the metal. So it's very important, guys, to understand what I'm talking about here. However, there is something that I actually want to address here. Since I said different metal has different cutoff frequency, it means different metal will have different what you call work function. So it means the work function, it is actually denoted, let me just talk about it, work function. What is the work function? The work function, it is the minimum energy that is needed to eject an electron from the metal surface. So it means the work function depends on the metal, not on the light. And to calculate the work function, we use the formula W naught equals to H multiplied by F naught. So you need to understand this. H multiplied by F naught. What is this F naught? The F naught is called the cutoff frequency. So it means when we are calculating the work function, we are calculating the work function of the metal, not of light. So it's very important to be able to understand what I'm talking about. Which means since we said speed of light, it's C into F times lambda, which means when we have F naught and lambda naught, we can still calculate the work function when we have cutoff wavelength, not cutoff frequency. So if we divide both by lambda naught to give us F naught, which means the work function now can be calculated by using HC over lambda naught. And guys, be careful. If we talk about lambda without the naught, we are referring to the wavelength frequency, the wavelength of light. But with the naught, it means it is the cut-off wavelength or the threshold wavelength. So it's called a threshold wavelength. Now, I want us to go deeper and understand what the relationship between the energy of photon and the frequency of light and the wavelength, and also the relationship between the work function of a metal. So which means different metals have different work function. Different metal has different work function. So it's very important, ladies and gentlemen, to understand this. Now let's go deeper. We know that when you're calculating the energy of photon, okay, let me use a different color. We know that when you are calculating the energy of photons, we use the formula E equals to HF if we're having frequency. But now look at this. H, it's always constant. It's constant, this one. So which means that if we want to change the energy of photon, we need to change the frequency of light. But if you look at this, these two expressions are actually directly proportional. What does it mean? It means higher frequency of light result to higher energy of photon. So what does this mean? It means if we want to increase the energy of photon, we need to increase the frequency of light. The energy of photon, the E, means that directly proportional. So the higher the frequency, the higher the E. The lower the frequency, the lower the E. But now, what did I say? I said when frequency is higher, it means wavelength it's shorter. So it means if we were to compare in terms of wavelength, we'll say the longer the wavelength, the lower the energy of photon. Why is it like this? Is because if we have a longer wavelength, frequency becomes higher. Longer wavelength, higher frequency. I mean, say lower frequency, I mean to say. And once we have lower frequency, it means the lower the frequency, the lower the energy of photon. So you need to understand this. So it means if you want to increase the energy of photon, you have to increase the frequency or you decrease the wavelength, because frequency and wavelength are inversely proportional. So it's very important to understand that. So it means they are directly proportional. But now let us now talk about the work function. How can we increase the work function or decrease the work function? We know that work function is calculated by using Planck's constant times the cutoff frequency F naught. And remember, the H is constant. So it means if I want to increase the work function, I have to increase the cutoff frequency. The higher the cutoff frequency, the higher the work function. And we know if the cutoff frequency is higher, it means wavelength it's lower. So it means higher cutoff frequency or threshold frequency result to higher work function. Will not. So if I want to increase the work function, I have to increase the cutoff, the cutoff frequency. Now, we go back to what I just said earlier, to say, not all the light can shine onto the metal, and yet the metal releases electrons. Sometimes it's possible that you find that the light can shine onto the metal, but you find that there is no electrons ejected onto the metal surface. What could be the reason for that? I want to explain it so that you can understand, ladies and gentlemen. Right. If frequency of light, that's a condition. Number one, if the frequency of the light, remember I said if I talking about F, you know we're talking frequency of the light. If the frequency of the light, if this light shine onto the metal, but you find that the frequency of the light, it's actually less than the cutoff, what is needed by the metal. If the frequency of the light, it's less than the cutoff, less than, not bigger than, but less than. What does this mean? It means that if the frequency of the light is less than the cutoff, can we multiply both by Planck's constant? This will give us HF. If I multiply both by Planck's constant, less than HF naught. And what is HF, ladies and gentlemen? HF on its own is the energy of photon, the E. Less than, what is HF naught? It is the work function. So it means that if the frequency of light is less than the cutoff, is the same as when we say the energy of light is less than the work function. I believe you're following. Which means that when the frequency of the light, or if the frequency of this light is less than what is needed by the work function, it means no electrons will be ejected. No electrons will be ejected. Why? It's because the energy of photon, or the energy that the light will produce, is less than what is needed, or the minimum amount of energy that the metal it require in order to eject electrons. So it means electrons will not be ejected. So conditions that will guide you to check whether electrons will be ejected or not is to check the frequency of light and the cutoff. If the frequency of light and the cutoff are not, like a frequency of light is less than the cutoff, it means energy is less than the work function, because I've multiplied both by Planck's constant. It means no electrons will be ejected. But secondly, if the frequency of light is exactly the same as cutoff, I want you guys to listen to me. If the frequency of light it's less than, it's equals to the cutoff, they are equal. Let's multiply both by Planck's constant. It means this will be HF equals to HF naught. And guys, what is HF? HF is just the energy of photon, is equals to the work function. You see that if the frequency of the light has the same frequency as the cutoff, then it means electrons will be ejected. Electrons will be ejected. But must be careful with zero kinetic energy. Electrons will be ejected, but with zero kinetic energy. We'll talk about this. Now, thirdly, if frequency is bigger than the cutoff, let's multiply both by Planck's constant. This is HF bigger than HF naught. And what is HF, guys? It is the energy of photon. So it means the energy of photon will be bigger than the work function. Obviously, if the energy of photon is bigger than the work function, it means electrons will be ejected. Electrons will be ejected. But this time around, with maximum kinetic energy. With maximum kinetic energy. With a maximum kinetic energy. That's why this last step, it is the one that leads to what we call the photoelectric equation. Because if the energy of photon is bigger than the work function, it means that there is an extra energy that will be added into the system. And that energy, it's called the kinetic energy. So now, let's now take this further to say, okay, fine. Because we know that when the frequency of light is bigger than the kinetic energy, like the cutoff frequency, electrons will be ejected with maximum kinetic energy. What does it mean? It means now, let's take the third one further to say, if the energy of the photon is bigger than the work function, it means that if we take the energy of the photon, we subtract the work function, there will be an extra energy added, which is called the kinetic maximum due to motion. So if we rearrange this, it means that the E is equals to W naught plus EK max. So this is called the photoelectric effect. I think they've shown it there. Whereby this photoelectric effect, we can calculate it by using E. We know it's HF, can use HF. W naught, it's HF naught plus the EK maximum. Or we can use this as HC over lambda. This side, it's HC over lambda naught plus the EK maximum. But we know when you're calculating EK maximum, this kinetic energy is just half mv maximum squared. So we use the kinetic energy formula. I believe you guys are following. But there's something that I want us to actually take it further. These conditions are very important to aid you to check that if the frequency of light is below the cutoff, no electrons will be ejected. But if the frequency of light is exactly the same as the cutoff, it means electrons will be ejected with zero kinetic energy. But if the frequency of light is bigger than the cutoff, it means that the energy of photon is bigger than the work function. So it means energy will be ejected with maximum kinetic energy. I want us to investigate further. Because this is very, very, very important, especially on the equation on the photoelectric equation. On the photoelectric equation, because there's something very important that one must be able to understand here. Let me write down the equation again. If we have E equals to W naught plus EK maximum, I want you guys to listen to me. Let's say now I want to compare the relationship between the E and the EK maximum. But this time around, I want to make W naught to be constant. Remember, the only way to make W naught to be constant is to make sure that your cutoff frequency is the same, or the lambda naught is the same. Now look at this. If I'm comparing E and EK maximum, assuming that W naught is constant, what is E? E is equals to HF. Then EK is just EK. I want you guys to look at this. The only way you can increase the kinetic maximum, if we assume that W naught is constant, is by increasing the frequency of light. So what does this mean? It means that the higher the frequency of light, and this is very important, the higher the frequency of light, the higher the energy of photon. and hence the higher the kinetic maximum. And this is very important, guys. Let me try to underline this. It means if we increase the frequency of light, the higher the frequency of light, let me just be specific, not the frequency of light. Remember, I said if you want to increase energy of photon, you need to increase the frequency of light. So the higher the frequency of light, the higher the energy of photon. So what does it mean? The higher the F, the higher the E. And the higher the E, the higher the EK max. If we assume that W naught is constant. So it means energy of photon and EK maximum are directly proportional. And these are exam typical questions, guys. You need to be able to that. If you want to increase EK max, you need to increase the frequency of light, or you decrease its wavelength, because remember, the higher the frequency, the lower the wavelength. They're inversely proportional. So it's very important for you to know this. Now, let's now do this. Remember, I'm assuming that we have kept what? We've kept the work function constant. Let's now compare work function and EK maximum, assuming that we are dealing with where the E is constant. This is the first condition. The second condition, let's now compare. I want us to compare work function and EK maximum. So let's say E equals to, it's minus W naught equals to EK maximum. So I've made EK maximum the subject of the formula. Here, my condition is that I want E to be constant. E is constant. And by the way, guys, the only way I can make E to be constant, it means to make the frequency of light constant. Now, look at this. If I'm comparing W naught and EK maximum, these two have a negative sign in between. This one, the sign is negative. I'm saying opposite sign, this one is positive. What does this mean? It means work function and the EK maximum are inversely proportional. Unlike frequency and unlike kinetic maximum and E. Kinetic maximum and E are directly proportional. So it means that because of the minus, it shows that the higher the work function, the lower the EK maximum. So the higher the work function, the higher the work function, the lower the EK max. It means they're inversely proportional. Work function and kinetic maximum are inversely proportional. I believe you guys are following. They're inversely proportional. They are inversely proportional. Work function and EK maximum are inversely proportional. So you need to be able to know these conditions when you are analyzing questions. So it means from now, if you want to increase kinetic maximum, you can increase the frequency of light, or you increase energy of photon, or you decrease the work function. That would be will have an impact towards energy of photon. I'm saying EK maximum. I believe, ladies and gentlemen, you are following. I strongly believe you are following. So now, let's do this. Let's say now, this time around, we are given, okay, we are given this scenario. Let's assume we want to look at the relationship between kinetic energy and the frequency of light. And guys, this is very, very, very important. This is an exam typical question. Obvious, if we write our equation, let's say we have E equals to W naught plus EK maximum. Let's make EK maximum the subject of the formula. It will be E minus W naught equals to EK maximum. I want you guys to listen to me very well. Which means that EK maximum depends on E and also W naught. But now let's assume we are having a metal which has same work function. Now look, let's make E is equals to HF minus W naught equals to EK max. If you look at this, if I rewrite this as I'm gonna say EK max equals to HF minus W naught. Obvious, this EK max here, it will be our dependent variable, will be the Y. So I want to compare the relationship between kinetic maximum and frequency, because this is an exam typical question. I want to do something like this. Let's say we have on a function, we have something like this. Okay, if we have something like this, guys, listen to me. On the y-axis, we'll have what you call EK max. On the x-axis, we have what you call frequency of light. Let me just say frequency of light. So I want to compare the relationship between EK maximum and frequency. Look, on the y-axis, my EK maximum, it is, on the y-axis, we have the EK maximum, and on the x-axis, we have the frequency. So this is the y, and this is the x. So what does it mean? It means always, if we construct, listen to me very well, if we construct the graph, this will be y equals to mx plus c, which means my y here, it is the EK maximum. Then the x is my frequency, this is the frequency. Then it means this is the y-intercept, this is the c, this value is the y-intercept. So it means always when we have the EK maximum and the frequency, if you sketch the graph will always be like this. Okay. And guys, you need to listen to me very well here. And if we construct this graph to the, like with the y-axis, the graph will have the y-intercept. Remember, the y-intercept, it's where x is 0. So now what is our x value? It means we have something like this. Let me try to use the dotted line. So it will touch the y-axis here. I want you guys to listen to me very well. So which means with y equals to mx plus c, the y is the EK max, the x is the frequency. Then how about this h here? The h is the one that represents the gradient. Then how about the minus W naught? It is the y-intercept, where we said we need the value of y when x is 0. What is the x? X is the frequency. So it means if we put, where there is frequency, we put 0. It means the EK maximum will be negative. So it means this is our W naught here, negative. So this is our y-intercept. And since that is our y-intercept, we have where the graph has touched the x-axis. This is called the F naught. It's where we have the cutoff frequency. which means any frequency that is above the cutoff frequency will release electron, because the frequency of light is now bigger than the cutoff. But if it's less than the cutoff, then it means no electrons will be ejected. So you must know from today, wherever you are given an EK maximum and the frequency graph, once you calculate its gradient between the EK maximum and the frequency, so it's going to be change in Y over change in Ix, which is the M. Our M here, it means the gradient between the EK maximum and frequency will be the H, will always be Planck's constant. So I believe you understand how I got this. So the y-intercept here is our work function. Then F is the X value, is the frequency. So it means F is the frequency, H is the gradient. So you need to be able to understand this graph. EK maximum and frequency, this is always called the cutoff frequency, F naught, we read it from here. So anything beyond that, then this eventually means now electrons will be ejected. I believe you're following. Now, let's take this further, guys. Let's say now we don't want to compare the relationship between kinetic maximum and frequency. We want to compare the relationship between kinetic maximum and the wavelength, kinetic maximum and the wavelength. Now, I want us to redraw that equation again. Now I want to compare the kinetic maximum and the wavelength. Not the frequency, but the wavelength. Let me show you. Kinetic maximum is still there. We do not change it. This is the EK max. Now we're talking about wavelength. How are we going to do that? We're going to say, okay, fine. E equals to W naught plus EK max. Let's make EK max the subject of the formula. So the EK max will be the E minus W naught. So the EK max will be, what is the E? It's HF minus W naught. But now we want to talk about the wavelength. So it means now we know C equals to F times lambda, which means F is equals to C over lambda. So we can substitute that. So we're going to have EK maximum equals to H into C over lambda minus W naught. So the EK, this will be, let me just say HC multiplied by 1 over lambda. 1 over lambda, not the X, I apologize. 1 over lambda minus W naught. You see that I've written this in the form of Y equals to mx plus c. However, from this Y equals to mx plus c, the Y is the EK max. Then this 1 over lambda is the X value. And this is the Y-intercept. So we still have the Y-intercept, but here we're going to say this is now talking about 1 over lambda. So it means if we use 1 over lambda, the inverse of the wavelength, the graph will still increase like this. Guys, but now what will be this point here? This point will be now called 1 over lambda naught. It is the 1 over the cutoff. So you know that if they give me 1 over lambda, the graph will always increase like frequency. But once they swap this, and oh, by the way, I forgot something. What is the gradient here? The gradient will be hc. It will not be Planck, but will be Planck's times the speed of light. So it means if you are calculating the gradient between the EK maximum and 1 over lambda, you must know the gradient, it's H times C. It's Planck's constant times the speed, unlike when we have kinetic maximum and frequency. So it means if we want only the graph for, listen to me very well, if we want the graph for EK maximum and with just the wavelength, not 1 over wavelength, it means you have to make the reciprocal of that. It means by making the reciprocal of that, the graph will change and become something like this. It will be a decreasing one, which means this will not be 1 over lambda, this will be lambda naught. So we know that when we are comparing kinetic friction, maximum and wavelength, just wavelength alone, there is an inverse relationship, and it's true. There is an inverse relationship between kinetic maximum and wavelength. But if we make 1 over lambda, it will have an increasing function. I believe you guys are following. More example will be dealt with. Yeah, I'm just explaining the concept. Now, one other thing that I need to talk about is the issue of intensity, guys. The issue of intensity is very important. Remember, you only change energy of photon when you change the frequency or the wavelength of light. Now, we want to go deeper and explain more about this. Remember, I said kinetic maximum versus frequency, the gradient is Planck's constant. Kinetic maximum versus 1 over lambda, which is going to give us HC as the gradient. Now, I want us to talk about the issue of intensity or the brightness. Guys, you need to understand something in terms of intensity or brightness. Increasing the intensity of light. I'm saying increasing the intensity of light without increasing the frequency. Let's assume we just have the light that is the same frequency. What we do, we just increase its heat intensity or brightness. Implies that, number one, it means more number of photoelectrons per unit time. So if the intensity of light is increased, it means we're going to have more number of photoelectrons per unit time that will be released. And because of that, as a result, which means there will be an increase in current. This will result to an increase in current or in the ammeter reading. Guys, you need to understand something here. Why is like this? Increasing the brightness do not have any impact towards the frequency of light. The frequency of light will still be the same. And because of that, the intensity just increases, or it causes the photoelectrons to be more per unit time. And because of that, it means there will be an increase in current or the ammeter reading. And mind you, no effect on the energy of light, energy of photons, or EK maximum. Remember, EK maximum is affected by the frequency of light and the energy of photon. So if we are just increasing the intensity without changing the frequency of light, it means, since we know that E equals to HF, frequency, if it's not changed, it means the energy of photon will not be changed. And if you're not changing the energy of photon, it means even kinetic maximum will still not be affected. So all the time in the exam, if you increase the intensity of light without changing the frequency of light, then you're not going to affect EK maximum. But if we increase the intensity at the same time we increase the frequency of light, EK maximum will be affected because we increase the frequency of light. So increasing the intensity or the brightness of a light only has an impact towards the number of photoelectrons per unit time and also the current. So that is what you need to know when you are dealing with intensity. Then, before I look at the questions, guys, let's now, let me just go through what I just said now in terms of the notes. Number one, let's check what I just said. We went through photoelectric effect. We went through, I'm saying in terms of its definition. We went through the significance of photoelectric effect, that if the frequency of light is less than the cutoff, no electrons will be ejected. But if it's exactly equal, they will be ejected at zero kinetic energy. Then if it's bigger than, they will be ejected with maximum kinetic energy. So now, what does this mean? It means that now we can move on to the issue of defining what is a threshold frequency or cutoff. We went through that work function. Remember, different metal have different work function. And we perform calculation, then we are going to do that. E equals to W naught by EK maximum. E is the HF. W naught is, we went through this, but there's something you need to understand. When we calculate EK max, we take the half times the square, the mass times the maximum, the square of the maximum speed of the electrons. So it means when you are calculating kinetic, let's say I want to calculate the maximum speed of electron, it means you must use the mass of an electron. It's given in the formula sheet. Lastly, you need to familiarize yourself with the effect of intensity and frequency on energy of photon. We went through frequency. Now we went through the intensity of the brightness. Brightness affect the number of photoelectrons per unit time and also the current. Right. Lastly, we have what we need to differentiate between atomic absorption and emission spectra. Guys, I want to explain this because this is an exam typical question. Let's go to the definition first. What do we mean by an emission and what do you mean by an absorption? Right. Then now, what do you mean by an emission? Right, let me start with an emission spectrum. When we say we have an emission spectrum, it means we are saying it is a spectrum that is formed when certain frequency of electromagnetic radiation are emitted due to the atom electrons making a transition from a high energy state to a lower energy state. If there's a transition in terms of energy state or energy level, that is called an emission spectrum. How does this occur, guys? Consider we have a prism. Let's say we have a prism. It's just an example. If we just have a prism and we just take a visible light or just a light with no gas in it, or it can be called a hot one. But now, if we take this light and we shine towards the spectrum, obviously, according to the way we know, when light shine onto the spectrum where there's no any gas involved, the light will release what you call the colors of spectrum, like a rainbow actually. colors of spectrum. So we'll end up having colors of spectrum. And these colors of spectrum, remember, they have different frequency and different wavelength. So we'll have something called Roig-B if we were to explain it according to rainbow. So it will be Roig-B. The last one, Roig-B. Okay. Roig-B. So it means now, you see that, like what I said in Doppler's effect, red is the one with the lowest frequency because it has the highest wavelength. Because of that, you see that these colors that are being released here, they have different energy level. They're at different energy level. Because we know the lower the frequency, the higher the lower the energy of photon. It's going to be low. So which means that when we move on to this will produce, will make a transition from a high energy level to a lower energy level. So because of that, this is an example of an emission spectrum. In other book, they call it the aligned emission spectrum. So it means this occur when certain frequencies of electromagnetic are emitted due to an atom electrons making a transition from a higher energy state to a lower energy state. So this is called the emission spectrum. But in terms of absorption is formed when certain frequencies of electromagnetism that passes through a medium, they pass through a medium, usually called gas, it's absorbed. So this is called absorption. So how does this happen? It means now we still have that prism, but among the prism, there's a medium here, and this medium, let's assume, is a cold gas. When it passes through a cold gas, is just an example. Then within that, let's say we still have that light. Let's say we still have the light. Then with this light, because it's now passing through the medium, it means because of that, the color, it will just produce a continuous line of colors. But depending on their bands. So because of that, it will not just produce all the colors like rainbow, but it will produce based on the medium. Now, this is an example of an absorption spectrum. So an absorption means the radiation must pass through the medium, particularly a cold gas, in order to produce the spectrum. So in the examination or in the paper, we'll be discussing this. So you need to be able to know which one is the emission and which one is the absorption line spectrum. I believe, guys, you are following. Then now it means now we will move on to the activities in order to answer the questions that we just addressed now. So we'll have to move on to the activities to address the questions that I just indicated so far. Hope, guys, you are following. Kindly don't forget to like, subscribe, and hit the bell notification. That will be much appreciated. Okay, we now continue with the questions for photoelectric effect. I'll start with activity number 1, which is question 10. It reads thus: a potassium metal plate is irradiated with light of wavelength 5 times 10 to the power minus 7 meter in an arrangement as shown below. So it means there is a light, and this light has a wavelength of 5 times 10 to the power minus 7 meter. It's not the cutoff wavelength, it's just the wavelength of the light. So here we're given the wavelength instead of frequency. Now, as shown below, the threshold frequency of potassium is 5.5 times 10 to the power 14. So it means this potassium has a threshold frequency of 5.55 times 10 to the power 14 hertz. What is this threshold frequency? It is the minimum frequency that is needed to eject an electron from the metal surface. So it means now we need to be able to relate this the threshold frequency or the cutoff frequency of potassium and the frequency of light to check whether the electrons will be released from a metal or not. And remember, if the electrons are released, then this ammeter will move from a 0 point, then it will show that there are movement of electrons along it. The current will increase from 0. So now it means that now we have to say, okay, because we are given the information, the first question says define a threshold frequency or a cutoff frequency. As I said, now that is the minimum amount of frequency that is needed to eject electrons from the metal surface. So we went through that. Then secondly, it says calculate the energy of photons incident onto the metal surface. Remember, we said to calculate the energy of photon depends on the light. So this is the energy of light, which is calculated by using a Planck's constant multiplied by frequency. But however, since we are not given the frequency of light, we are given the wavelength, so we can use the formula hc over lambda, because now we are given the wavelength. So now to do the calculation, we'll say the energy of photons is the Planck's constant times the speed of light divided by the wavelength, because we're given that. So what is Planck's constant? Planck's constant is 6.63 multiplied by 10 to the power minus 34, if I'm not mistaken, multiplied by the speed of light in a vacuum, it's 3 times 10 to the power of 8. Then we divide this by the wavelength, which is 5, multiplied by 10 to the power minus 7. So now we can work out the energy of photon. So this will be 6.63 times 10 to the power negative 34, multiplied by 3 times 10 to the power of 8, divided by 5 times 10 to the power negative 7. So this will give us the energy of photons to be 3. If we round into 2 decimal places, it will be 3.98 times 10 to the power minus 19 joules. It's an energy, so it should be measured in joules. So now we know the energy of photons, but we can still calculate using the frequency. However, we'll have to convert from wavelength to frequency, but it's just a waste of time based on the question. So now we went through the workings. Then now, without wasting time, where did I get the Planck's constant and the speed of light? From the formula. If you can just check down here, let me go down on the formula sheet. Actually, the physical constant table. You'll see that we have the speed of light in a vacuum. Speed of light in a vacuum, it's 3 times 10 to the power of 8 meters per second. whereas Planck's constant is 6.63 times 10 to the power negative 34. I believe you are following. Let's now go back to the question. Now, we know that in terms of the energy of photon, as I said, energy of photon depends on the wavelength and the frequency of light. So let me say the wavelength and the frequency of light. We know that the higher the frequency, the shorter the wavelength. So it means the higher the frequency, the higher the energy of photon, because they're directly proportional. And the lower, the shorter the wavelength, the higher the energy of photons, because in that case, they will be inversely proportional. I believe you understand. Lambda, if it's longer, energy of photon becomes shorter. I'm saying, or becomes lower. So they're inversely proportional. Right, now we've answered the first and the second. Let's move on to the next question. It says, prove that the ammeter will show reading. Remember, the ammeter will only show reading if there are electrons that are being ejected. If there are electrons that are being ejected, then the ammeter will actually show the reading. So let's now check whether the electrons were ejected or not. Remember, I said something earlier to say we can check whether electrons will be ejected or not by comparing the frequency of light and the cutoff frequency. If the frequency of light is actually greater or equals to, let me just say greater or equals to, but now in this instance, we'll say if the frequency of the light is above the cutoff frequency, it means that electrons will be ejected. And another way, how can we check this? If we multiply both by the Planck's constant, this will be HF bigger than the HF naught. And we know HF alone, this is the energy of photon. And if the energy of photon is above the work function, this is our work function, then it's another way to say, to indicate that electrons are actually ejected. And if electrons are ejected, it means the ammeter will start reading. It will move from 0 point and will increase in terms of the current. It will show that there is a flow of electrons in the connection. Right, without wasting time, ladies and gentlemen, let us now work this. Now, since already we know the energy of photon, we can say now we know the energy of photon. Let's now calculate the work function. To calculate the work function, we are given the cutoff frequency. So we can say the work function is the Planck's constant multiplied by the cutoff frequency. Now, what would Planck's constant? 6.63 times 10 to the power negative 34. We multiply this by the cutoff frequency, which is 5.55 times 10 to the power 14 hertz. Then let's now multiply this. So it will be 6.63 exponential negative 34. We multiply this with 5.55 times 10 to the power 14, if I'm not mistaken. So this gives us the work function of 3.68 times 10 to the power minus 19 joules. Now we want to compare the energy of photon and the work function. Which one is higher? Already you can see that the energy of photon is higher than the energy of, I'm going to say the work function, or the minimum amount of energy that is needed to eject electrons from the metal surface. In that case, I apologize. The one which is bigger in terms of this one, let me check something. Okay, 3.98 times 10 to the power minus 19, subtract 3.68 times 10 to the power minus 19. Obvious, it means now we're going to say, since the energy of photon is bigger than the work function, which means that electrons will be ejected. Electrons will be ejected, actually with a maximum kinetic energy. And since electrons will be ejected, it means the ammeter will show a reading. So this is how we can check that. One other way of doing that, we can still do this. We can still calculate the frequency of light if we do not want to use that approach. We can say, since we are given the wavelength and we are not given the frequency of light, we can calculate frequency of light by using the speed formula, which says speed of light is equal to frequency multiplied by the wavelength. Now, what is the speed of light in air? Is 3 times 10 to the power of 8, or 3.0. We do not know the frequency, but we know the wavelength. It's 5 times 10 to the power minus 7 times frequency. Then we make frequency the subject of the formula. It's 5 times 10 to the power minus 7, and we divide there by 5 times 10 to the power minus 7, and these two will divide. Then we get the frequency of light, not the cutoff frequency. So it's 3 exponential, 3 times 10 to the power of 8 divided by 5 times 10 to the power minus 7. So this will give us a frequency of light of 6 times 10 to the power 14. So you can easily see that the frequency of light is bigger than the cutoff, because its cutoff is 5.55. This one is 6 times 10. So it means same applies. Electrons will be ejected with maximum kinetic energy. But even if you do not write this, you're still they will still allocate marks for you, because here we want to check whether electrons will be ejected or not. So the electrons will be ejected, and since the energy of photon is bigger than the work function, or since the frequency of light is higher than the cutoff, then it means electrons will be ejected. And if electrons are ejected, means the ammeter reading will start to do what? To read. It will start to read. We'll move from 0 to a certain point, which means the ammeter will show a reading. So this is what we were expected to say, right? In terms of like using calculations, right? Then okay, let me just say, one other way we can still compare this using the wavelength. Remember, it means the only way, if the wavelength of the light is less than the wavelength of the cutoff frequency, then we can also comment using that. There is no problem with that. Right, then now, let's now move on and try to answer the last question, 10.4. Right, 10.4 says the intensity of light is now increased. The intensity of light is now increased. Remember, I spoke about the issue of intensity or the brightness. Intensity or the brightness. Since here we are just increasing the intensity of light, intensity affects the current, the amount of current actually that will be read from the ammeter. So which means that here, the question says the intensity of light is now increased. Explain why this change will cause an increase in the ammeter reading. Right, number one, you will say an increase in intensity of light, or in the intensity or the brightness of light. An increase in the intensity or the brightness of light, it means more photoelectrons per unit time. And if there are more photoelectrons per unit time, it means the current increases, then hence an increase, hence an increase in the ammeter reading. Remember, guys, intensity has no impact on the kinetic maximum or the energy of photon, unless if we're increasing the intensity and at the same time changing the frequency. That frequency will have an impact on kinetic maximum or energy of photon. But when we're talking about intensity, guys, intensity has nothing to do with the frequency of light, because we're just increasing its brightness. We're not changing the frequency. So it's very important to know that, like when they talk about this, you are able to comment in terms of this. This is one of the easiest topic, guys, but you need to understand. Remember, practice makes perfect. I believe you are following. And guys, in the exam, be able to differentiate between the light and the metal, because sometimes you find that someone can take, you see here they've been specific to say this is a threshold. You know, this has to do with metal, not the light. So it's very important to know that. Okay, it's very, very, very important to know that. And in terms of this, we can also calculate the EK maximum if you wanted to know the EK maximum, depending on this. Remember, the energy of photon was 3.98 times 10 to the power minus 19 joules, which means if we use the photoelectric equation, or if we use the photoelectric equation, electric effect equation, we can say energy of photon equals to the work function plus the kinetic maximum. Then we know the energy of photon, we have calculated it is 3.98 times 10 to the power minus 19. I'm just adding this question, guys. What is the work function? The work function is 3.68 times 10 to the power minus 19 plus the EK max. I'm just adding this question, guys. Remember, I'm not just teaching you just to answer this question, but just to be able to know what we're actually doing. So we can make EK max the subject of the formula. It means the kinetic maximum here. Sorry, I apologize. The kinetic maximum here will be 3.98 minus 3.68 times 10 to the power, I'm saying 3.98 exponential to the power minus 19 minus 3.68 times 10 to the power minus 19. This has to do with 3 times 10 to the power negative 20 joules. And you can still use this property when you're commenting whether electrons will be ejected or not by looking at EK max. This is another way to say if the EK max is bigger or equals to 0, electrons will be ejected, especially if it is bigger than 0, it means more electrons will be ejected. So you see, that was one can say, since the kinetic maximum is bigger than 0, electrons will be ejected. That is another way of commenting on this question. Yes, on this question. Remember, there are many ways to skin a cat. And again, we can even be able to know what is the speed of that electron. What is the maximum speed of that electron that is being ejected? To do that, we know kinetic energy, the formula, it's half mv squared. But since here we're talking about electrons, it means you're going to talk about the mass of electron, and this will be the maximum velocity or the maximum speed of an electron. So what is the kinetic maximum? We know is 3 times 10 to the power negative 19. Half multiplied by, we need to know the mass of an electron. The mass of an electron is given in our formula sheet. Let's just go down and look for that. This is just an arrangement, like I just added the question. Where is it? Okay, there it is. The mass of an electron, yes, electron mass of an electron. Where is it? There it is. Electron mass, it's 9.11 times 10 to the power negative 31. 9.11 times 10 to the power negative 31. That is the mass of an electron. So we're going to substitute where there is mass of an electron. Okay, guys, I apologize. Right, which means now, oh, sorry. Okay, so what would be the mass of an electron? As I said, the mass of an electron is 9.11. 9.11 times 10 to the power minus 31 times the square of this velocity or the speed. So now we can work this out by saying, okay, fine. We have to make v squared max as the subject of the formula. So we're going to have 3 times 10 to the power minus 19. This time around, we're going to say 0.5, which is half multiplied by 9.11 times 10 to the power negative 31. So this will give us let's just say 56 times 10 to the power minus 31 times the V max squared. So let's make V max squared the subject of the formula. So we're going to have, we divide both by 4.56 times 10 to the power negative 31, because we want to make V max squared the subject of the formula. So it means the V max squared would be 3 times 10 to the power negative 20 divided by 4.56 times 10 to the power negative 31. This gives us V max squared of 6.58 times 10 to the power 10. Then we put the root sign to determine the speed of the electron. And so it will be square root of 6.58 times 10 to the power 10. Then this will give us 256.515.11 meters per second. So this is the answer. But remember, guys, practice makes perfect. It's not included there. I just added it, guys. Right, let's now move on to the next question. Oh, okay, sorry. Let's now move on to the next question without wasting time. Okay. Before we look at this one, okay, fine. Let's just go through it, because I wanted to do a different one, which is based on graphs. Right, without wasting time. Okay, let's just look at this one. Let us look at this one. Okay. I'll just check. It says a simplified diagram of an apparatus for an experiment to investigate the photoelectric effect is shown below. Light of a fixed frequency. Light of a fixed frequency. And this is very important, guys. Light of a fixed frequency. It means a light that has fixed frequency that is not changing. It's incident onto the cathode of the photoelectric tube. So it means if we're conducting experiment, what will be a controlled variable? It will be a frequency of light. I mean, if we're conducting experiment, this will be a frequency of light or the energy of photon, right? Then now, if a light of a fixed frequency is incident during an experiment, the ammeter registered the photo current. You see, as I was saying, this is just an experiment. Okay, fine. Then now, during an experiment, okay, photo current, right? The current, fine. Then now, the first question says define the term photoelectric effect. I believe we went through that. That is the process whereby electrons are ejected from the metal surface when light of a suitable frequency is incident onto the surface. So it's very important to be able to know that. Now, look at this. Now they said the intensity of the incident light is increased. What they say? Intensity has to do with brightness. So we're increasing the brightness of the light. We're not increasing the frequency. We're just increasing the brightness of light. So now, what's going to happen? I think we just addressed the question in the previous question. So I'm not gonna go deeper into this. So right, then now it says state how this increasing intensity will affect the ammeter reading. The ammeter means this has to do with, it's used to measure current. Obvious. What would be the answer? Let me just give you a second to just decide. I hope you got the answer. The answer is increase. The ammeter reading will increase. Why? An increase in intensity implies more photoelectric, more photoelectrons per unit time, which will result to an increase in current. And if there is an increase in current, it means the ammeter reading will also increase. So I believe you understand this one. Now we can move on to the next question because I know you understand this. Right. Then now the next question says, when frequency of the incident light, we're talking about incident light, when the frequency of light, so this is the frequency of light, it's not cut off, it's F, not F naught. So we're given F, which is 5.9 times 10 to the power 14 hertz. And again, when the frequency of light is this, the maximum recorded kinetic energy of photons is given by this. So we're even given the EK max. We're given the EK max, it's 2.9 times 10 to the power negative 19 joules. Remember, when we're given EK max, we can be able to know what is the speed of that electron that is being ejected. Right, then now, the question says, calculate the what? Calculate the maximum wavelength or the threshold wavelength of the incident light that will emit an electron from the cathode of the photoelectric tube. We want to calculate lambda naught, which has to do with the metal, not the light. Lambda naught, we need to calculate lambda naught, the threshold wavelength. So how are we going to do that? Straightforward. What we do is we just say, okay, fine. Let me just go down here, guys. Okay, it's okay. So we can say, let's write the formula. Energy of photon, it is the work function plus the EK maximum. Now we can calculate the energy of photon. We know the energy of photon. It's either we calculate it direct or we calculate separate. There's no problem. So energy of photon, it's H times the frequency of light. What is blank? It's 6.63 times 10 to the power minus 34. Let's multiply this with the frequency of light. It's 5.9 times 10 to the power 14. But we have to show this in your workings, in your exam, right? But you can even substitute them, right? So we're going to have 6.63 times 10 to the power minus 34 multiplied by 5.9 times 10 to the power 14. So this gives us the energy of photons to be 3.91 times 10 to the power negative 19 joules. Let's do the substitution. We have energy of photon is 3.91 times 10 to the power negative 19. We do not know the work function, but what do we want, guys? We want the threshold wavelength. Remember, there are many ways to skin a cat. Here, what we can do, just for simplicity, let's just make the work function. What is the EK maximum is 2.9 times 10 to the power minus 19. Let's now make work function the subject of the formula. There are many ways to skin a cat. So 3.91 times 10 to the power minus 19, subtract 2.9 times 10 to the power minus 19. This will just give us a work function of 1.01 times 10 to the power negative 19 joules. But it's not what we want. We want to calculate the cutoff wavelength. The cutoff wavelength. The cutoff wavelength is what we want to get. So to do that, it means we're going to say we know that cutoff wavelength, work function is equals to the Planck's constant and the cutoff frequency, but we don't want this. We want the one where there is a cutoff, so it's going to be HC over lambda naught. Is there in our formula sheet. So let's do the substitution to calculate this. Right, we're going to have what is the work function. Or in the meantime, okay, let's just substitute, but in the meantime, we can still, okay, fine, let's just substitute. What is the work function? 1.01 times 10 to the power minus 19 equals to, Planck's constant is 6.63 times 10 to the power minus 34. What is the speed of light? 3 times 10 to the power of 8 divided by lambda naught. So we can make this one to be a fraction and we cross multiply. So this will be 1.01 times 10 to the power minus 19 times lambda naught, which is the cutoff wavelength. Then we multiply 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power of 8. So this will give us the value of 1.99 times 10 to the power negative 25. So we can divide both by this 1 times 10 to the power negative 19, 1.01 times 10 to the power negative 19. Then this will give us our cutoff wavelength. So 1.99 times 10 to the power negative 25 divided by 1.01 times 10 to the power negative 19, if I'm not mistaken. So this will give us 1.97 times 10 to the power negative 6 meter. Negative 6 meter. There are many ways to skin a cat, guys. There are many ways to skin a cat. So this is not the only approach. This is not the only approach. There are many ways to skin a cat. So we've now answered the question where they required us to calculate the cutoff wavelength. We can even make a direct substitution rather than just writing it separate. We can even do that. Another way would be, we can still do this and say energy of photon is the work function plus the EK max. Then we know we have calculated this. This is how much? 3.91 times 10 to the power minus 19. Then we know this is HF naught plus, what is the EK max? It's 2.9 times 10 to the power negative 19. So what we can do here, we can, oh no, not the F naught, guys, I apologize. Oh yes, it's F naught. Then what we can do here, we can say, okay, right, let's now calculate F naught rather than calculating lambda naught. So we're going to say we transpose 2.9 times 10 to the power negative 90 to the left-hand side. It will still give us 1.01 times 10 to the power minus 19. Then we know Planck's constant is 6.63 times 10 to the power minus 34 with the cutoff. Then we first calculate the cutoff. It's still fine. There are many ways to skin a cat. So 1.01 times 10 to the power negative 19. Then we divide by 6.63 times 10 to the power negative 34. This will give us a cutoff frequency of 1.52 times 10 to the power 14 hertz. And since we do not want cutoff frequency, we want the cutoff wavelength, we use the speed equation, which says speed equals to F times lambda. We're gonna call it lambda naught. I'm say F naught and lambda naught. So what is the speed of light? 3 times 10 to the power of 8. Lambda naught, it's 1.52 times 10 to the power 14, then lambda naught. So I'm saying F naught. So let's now divide by 1.52. So 3x times 10 to the power of 8 divided by 1.52 times 10 to the power of 14. To the power of 14, this will still give us 1.97, 1.97 times 10 to the power minus 6 meter. Still, there is no problem with that. It depends on what you're actually given, guys. It depends on what you're actually given. Right, let's now move on. Let us now move on. Right, let me erase this. Okay, before we erase, let's just go down. Oh, we cannot be able to see. Okay, right. I believe, guys, you are with me and you are following. Please don't forget to like, subscribe, and share the videos with others. Right, then now, if there's any question or you don't understand a thing, kindly make a comment in the video, then I will make sure that I attend to you as soon as possible. Because like right now, there's one learner who asked me to create this video of photoelectric effect. So that is what I'm actually doing now. So please don't be shy to keep in touch with me. Right. Without wasting time, let's now move on. Then the next one says the maximum kinetic energy. The maximum kinetic energy of electrons, of photoelectrons, increases when light of higher frequency it's used. When light of higher frequency it's used. The maximum kinetic energy of photoelectrons becomes higher when the light of higher frequency is used. Use the photoelectric equation to explain this. Listen, guys. According to the photoelectric effect, we know that energy of photon equals to the work function plus the EK maximum. So now here we are, we want to compare, we want to know, like, when the maximum when this EK increases, it increases when the light of frequency is used. Now let's talk about this. I'm going to say this: the higher the frequency of light, the higher the frequency of light. I'm now comparing frequency of light with the energy of photon, because we know energy of photon equals to HF. The higher the frequency of light, the higher the energy of photon. The E. If the frequency of light becomes higher, it means the energy of photon also will be higher. And as a result, the higher the energy of photon, the higher the kinetic maximum. They're directly proportional. So you see that kinetic maximum will increase if the light, or if light of a higher frequency is used. So now we are comparing kinetic maximum and the frequency. And remember, when you're comparing, that means you must talk about frequency and what, and the energy of photon. They're directly proportional. And if the frequency is higher, the energy of photon has to be higher. And if the energy of photon is higher, then the kinetic maximum has to be higher. Here it means we are not talking about work function. It means the work function here is constant. I believe you're following, ladies and gentlemen. I believe you're following. So they are directly proportional. Okay. I believe, guys, you are following. Remember, practice makes perfect. Practice makes perfect. Let's now move on to the next question. Next question, ladies and gentlemen. This has to do with graphs. All right, let's now look at this. It says in the photoelectric equation, light of different frequency was radiated. Light of different frequencies was radiated on each two metals. So we had two metals actually. We had metal, according to the question, there are two metal A and metal B. So metal A and metal B. And they actually used different frequencies. So they said different frequencies was radiated on each of these metal. So it means there was a light, and this light shine onto the metal, and another light here, but of different frequency also shine onto this metal. All right. Now, here they're saying the graph of kinetic maximum energy of the ejected electrons from metal A, and the frequency of the incident or of the light photon, it's shown. So here we are given the graph for the EK max and the frequency. And I think I just said something earlier to say, all the time, if they give you a graph for the EK maximum and the frequency, then the graph should be increasing. And where the graph touches the x-axis, it is the point where the kinetic maximum is 0. And if the kinetic maximum is 0, it means that the energy of photon is the same as the work function. And it also means that if we remember this HF, this is HF naught. So it means if we divide both by the Planck's constant, it means the F equals to this. So it means this is the point where the frequency of light is the same as the cutoff. So it means this is where we have a cutoff frequency at this point here. This is where we have the F naught. And if we reconstruct this, maybe up until it touches the y-axis, it means this will be the work function, but it will be a -1. This is the y-intercept. So, and what did I say? Whenever you have, remember, according to what I said, when you have y equals to mx plus c, if we rearrange this, the y will be the EK max. And from our equation, you'll see that the HF, it will be, we're going to have HF here minus W naught, according to the equation, because this is energy of photon. So it means now, here we are comparing, what is the y? The x is the frequency. So it means this is the gradient. So it means when you are given on the kinetic maximum and frequency graph, once you calculate the gradient between kinetic maximum and frequency, it will give you a Planck's constant. It will give you a Planck's constant. I think I've explained this. Now, if you look at the graph, it says point X on the graph represent an unknown kinetic maximum. So you see, if it's representing an unknown kinetic maximum, it means this point here, it's actually the frequency of light, because here, this is the cutoff. So it means you already have a cutoff frequency of 5 times 10 to the power 14 hertz because of this. So it means the F, this 12.54, it is the frequency of light. You see that electrons will be ejected, because you see, if this is the EK maximum, it's already bigger than 0, so it shows that electrons will be ejected. So it means any frequency that is below 5, there will be no electrons that will be ejected. I mean, of light. I believe you are well. Right now, let's now go through this question. Now, the first question says, write down the numerical value of the gradient of this graph. What did I say? When you have a kinetic maximum against the the frequency graph. Once you calculate the gradient will be Planck's constant, the Planck's constant. But since they say write down the numerical value, so it means you're going to say the Planck's constant, it's 6. Actually, you can say the gradient. So the gradient will be 6.63 times 10 to the power minus 34. So we've answered the first question. Then the second question says, define the term work function. Work function is the minimum amount of energy that is needed to emit an electron from the metal surface. I believe you're following. Then the next question says, now calculate the work function of metal A. Remember, work function depends on the cutoff frequency or the cutoff wavelength. The higher the cutoff frequency, the higher the work function. Now let us now calculate that. So this will be 6.63 times 10 to the power minus 34 multiplied by the cutoff frequency. We have that it's 5 times 10 to the power 14 hertz. So let's now calculate the work function. So it's 6.63 times 10 to the power minus 34 multiplied by 5 times 10 to the power 14. So it means the cutoff, the work function will be 3.32 times 10 to the power negative 19 joules. Now we have calculated that. Then now the next one, it says, now we need to do what? Now we need to calculate the value of X. What is the value of X? Is the kinetic maximum. So we can do that. Okay, so okay, fine. What is the photoelectric equation? Electric effect equation. It's E equals to W naught plus EK max. Want to know what is the EK max? And to do that, already we have the work function. We have calculated the work functions. What we need is just the energy of photon. So we can say, okay, fine. HF equals to W naught plus EK maximum. What is the Planck's constant, ladies and gentlemen? 6.63 times 10 to the power minus 34. And what is the frequency of light? It's 12.454 times 10 to the power 14. Work function we already have, it's 3.32 times 10 to the power minus 19 plus the EK max. Let's now do the working of this. So it's 6.63 times 10 to the power minus 34 multiplied by 12.54 times 10 to the power 14. So it means this will give us a work function. I'm saying the energy of photon to be 8.31 times 10 to the power minus 19 equals to 3.32 times 10 to the power minus 19 plus the EK max. This is what we want. So what will be the EK max? The EK max will be, we can transpose 3.32, so it's 8.31 times 10 to the power minus 19 minus 3.32 times 10 to the power minus 19, which is just 4.99. 4.99 times 10 to the power minus 19 joules. So this is the value of X, which is roughly 5. I believe you are following, guys. I believe you are following. And remember, there are many ways to skin a cat. Like one can do this, but already since we are, but already we have the answer 6.63 exponential to 0.34, 12.54 exponential negative 19 minus 5 exponential, as not negative 19, but 14. 14 minus 5 exponential 14. Close the brackets. The same applies. 4.9 now, which is just roughly 5. Okay, right. Then now I believe you guys are following. I believe you're following. Okay, let me raise this first. Don't forget, guys, that practice makes perfect. If you practice as many questions as possible, I'm telling you, you will enjoy Physical Science paper 1. Okay, then now let's move on. The next one says, how will each of the following be affected if the light of frequency of 12.54, if the light of frequency of 12.54 times 10 to the power 14, still the same light of this one, but of higher intensity it's used. You see that they did not change the frequency. The frequency is still the same. The frequency of light is still controlled, still the same. They've used the same frequency of light because initially they've used 12 point. Now they just increase in intensity. Then choose increase, decrease, or no effect. The value of X. What is the value of X? EK maximum. We know intensity affects the number of photoelectrons emitted per unit time and their current. So it means there will be no effect here. Unless if they've changed the frequency of light, then they will affect the EK maximum. But the number of photoelectrons emitted per unit time will actually increase. This one, there's an increase. I think, guys, you are following. I believe you are following. You are following. Then the second one is says, or the last question I meant to say. It says metal B has a larger work function than that of metal A. Redraw the graph in your answer book. Do not include values. Label as A, and also in the same set, you draw the graph of B, metal B, and label as B. Look at this, guys. Here is just a matter of understanding. If we can look at this, guys, we are told that metal B has larger work function than metal A. Let's look at the factors that actually affect work function. Number one, when we calculate work function, it depends on the cutoff frequency or the wavelength, cutoff wavelength. So it means the higher the cutoff frequency, the higher the work function. So what does it mean? It means metal A, what is its cutoff frequency? It's 5. So if metal B has larger work function than A, it means its cutoff frequency is actually higher. So it means it should be above 5. So it means when we draw the graph, we're going to say, okay, fine. Here it's our graph. This one is the EK max. And this one is the frequency in hertz. Already we have for A, let's just label this as A, because they said we mustn't show value. The cutoff frequency of A is this one. So it means if we increase the cutoff frequency, maybe it's somewhere there, the work function of that metal will actually increase, because the higher the cutoff frequency, the higher the work function, or the larger the work function. So which means that this one is it will be for B, because its cutoff frequency is bigger than that of A. But don't forget, if we were to compare the work function and the kinetic maximum, what did I say? Like if I say E minus W naught equals to EK max, Because of this minus, I said there's an inverse relation between work function and EK maximum. So it means the larger the work function, the smaller the EK max. So between metal A and metal B, which one has higher kinetic maximum? Obvious, the one with higher kinetic maximum is the one with the lower work function. So it will be metal A, because metal A has smaller work function as compared to B. So the smaller the work function, the higher the kinetic maximum. But it's not part of this. So I was just adding it, actually. I strongly believe, guys, you are following. I believe you are following. Okay. Without wasting time, let's now move on to the next question. Okay, this one actually I will not do it with you because I believe I've done as many questions as possible. Like I just did one example now. So what you can do, just try to pause the video and do it on your own. You see, we have two metals there, sodium and silver. Each has, you can see there, it has different cutoff frequency. So I'm not gonna tell you, just try to go through it on your own, and calculate and check the answer. Like, the thing is, I don't want to do it with you now because I've already addressed it in the previous example. But however, it's fine. Let's just do it because already you'll not be able to know where we get the answer. Okay, that's fine. Let's just go through. Elena is investigating photoelectric effect of two different metals, silver and sodium, using light of different frequencies. The maximum kinetic energy of the emitted photo is plotted against the frequency of light. You see, we are still comparing kinetic maximum frequency of light for each of the metals as shown. Define the threshold frequency. I believe you can do that. Which metal between sodium or silver has a larger work function? Obvious, the answer is silver. Why? Because the cutoff frequency of sodium is 5.94 times 10 to the power 14, then this one is. So it means this one has a larger, or it has higher cutoff frequency. And remember, we said work function depends on the cutoff frequency or the cutoff wavelength. So since this one has a higher, it has higher cutoff frequency, it implies that even the work function will still be high. I mean, if we want to respond to that, so the answer would be silver. But what if they said which one will have higher kinetic maximum between silver and sodium? Obvious, the answer will be sodium, because when we are relating work function and kinetic maximum, because of the minus, it means there's a negative relation between work function and kinetic maximum. If we're using the same light, if we assume that energy of photon is the same, so it means the lower the work function, the higher the kind. So it means sodium is the one which will be higher, which will have a higher EK max. I mean, if they ask, they've asked you a question. Name the physical constant represented by the slope. Obvious, this is Planck's constant. Name. So you're gonna say Planck's constant. Then it says if the light of the same frequency is shine onto the metal. You see, the light of the same frequency is shine onto the metal. In which metal will the ejected photoelectrons have a larger maximum kinetic energy? I think I've explained the answer. Why? Because now, number one, same frequency of light. Same frequency of light implies same energy of photon. Energy of photon, E. And according to this, these two metals have different work function. We know the what? The larger The larger the work function, the lower the EK maximum, because they're inversely proportional. So now the question says, which metal will have the larger EK max? Which one? It will be sodium. Sodium, because it has smaller work function than silver. And the smaller the work function, the higher the EK maximum. I think I just addressed that. Okay, then now let's move on, guys. Let's move on. How about if we had, we're not given frequency and we're given the wavelength. Remember I said if we're given the wavelength, we should be behaving a decreasing function. A decreasing function. So it means the function will be something like this. This will be the lambda naught. But if we make 1 over lambda, then it will still be an increasing. Okay? I believe you guys are following. But I've addressed that in the first slide. All right. Yeah. Now we're moving to the issue of emission of spectrum. I think this will be the last question. Will it be the last question? Yes, it will be the last question for this session. Okay, guys. Let's now go through this. Remember we spoke about the issue of emission, spectrum, and absorption, where we said emission especially occur when there's a transition of energies, particularly from a higher energy state to a lower energy state. But the absorption is the one that's actually the radiation occurs when the radiation passes through the medium, particularly when we have like cold gases. So here you can easily see that, okay, fine. It says the teacher is in a science class, explain how different types of spectra are obtained. The teacher uses the simplified diagram shows alongside for the explanation. Name the type of the spectra. If you look here, we just use light, this visible light, okay? And it's just shining on a diffraction or on a prism. Obviously, this will produce the spectrum of colors of spectrum with different frequencies and different energies. So which means this will be emission. We actually call it a line emission of spectrum. Right, then this one, since this is just a light that it's passing through a medium, and this medium, which is called gas, like to absorb that energy of light, then what is going to happen? It will just produce, it will just produce specific bands depending on the light. So which means this will be absorption. Absorption spectrum. So it means we know what is Y. Y it's emission, then Z it's absorption. I think we explained that. I've explained that in the previous slide. Right, without wasting time, ladies and gentlemen, let's just move on. Remember, practice makes perfect. Okay. Now let's move on, ladies and gentlemen. 10.2 says, in an excited atom, electron can jump. It's true. Electron can jump from a lower energy level or energy, yes, energy state or energy level. In an excited atom, an electron can jump from a lower energy level to a higher energy level. They can also drop from a higher energy level to a lower energy level. So the diagram not drawn to scale shows some of the transition of electron in an excited atom. If you look here, when you go up, it means this is an increasing in terms of energy. So this is energy level 2, level 3, level 4. So it means you are moving from a low energy level to a higher energy level. But this time around, it shows that it implies that we're moving from a lower energy, a higher energy level to a what? To a lower energy level. This has to do with emission. Right. Then now, do the transition indicated in the diagram leads to absorption or emission? The answer is emission, because emission has to do with where the transition is moving from the higher energy level to the lower energy level. Then the question says, now calculate the frequency of photons that are produced when an electron in an excited electrons transit from E4 to E2, from E4 to E2. So we need to get the difference in terms of that. So we have to get the difference in terms of energy level. So it means the energy level or the energy of photon will be the E4 minus the E2. We get the difference of that. So we're going to have 2.044 times 10 to the power negative, is it 18? Then minus 1.635 times 10 to the power negative 18. So we are going to get the energy of photon. So this will be 2.044 times 10 to the power negative 18, subtract 1.635 times 10 to the power minus 18. So this will give us the energy of photon to be 4.09 times 10 to the power minus 19. So now joules, minus 19 joules. I believe you guys are following. I believe you guys are following 1.635. So now, times 10 to the power minus. Okay. I want to say something 2.044. Okay. So now since we have the E, we can get we want the frequency of photons. So it will be E equals to HF. We know the energy of photon is 4.09 times 10 to the power negative 19. Planck's constant, it's 6.63 times 10 to the power negative 34 times the frequency. Then we divide both by 6 point. So it's 4.09. 4.09 divided by 6.63 exponent times 10 to the power negative 34. It means the frequency of the photon will be 1.17. Oh, no, not less than 1.17. I apologize, guys. 6.17 times 10 to the power 14 hertz. 14 hertz. 14 hertz. So this is the frequency of photon produced when an electron in an excited also makes transition. Right, moving on, then the second statement says the threshold frequency of the metal Q, it's 4.4 times 10. So we're given F naught. So F naught, it's 4.4 times 10 to the power 14 hertz. Then we are asked to, like the question says, calculate the kinetic energy of the most energetic electron. Most energetic electron ejected when photons produced in question point 2.2 is incident onto the, so it means it's just a continuation to say we have the E, equals to W naught plus the EK maximum. So this one, we just calculated it now. The energy of photon we have is 4.09 times 10, 10 to the power minus 19. The work function, we know this one is HF naught. So HF naught, so it's going to be 6.63 times 10 to the power minus 34. Then we multiply this by the cutoff frequency is 4.4 times 10 to the power 14 plus the EK max. So let's do the working. 4.09 times 10 to the power negative 19. So this time I'm going to say 6.63 times 10 to the power negative 34 multiplied by 4.4 times 10 to the power 14. So this will give us 2.92 times 10 to the power minus 19 plus EK max. So we can now calculate the EK max. So what would be the kinetic maximum energy? So it will be 4.09 times 10 to the power minus 19 minus 2.92 times 10 to the power minus 19, not 18, I apologize. Okay, so it will be 4.09 exponential negative 19 minus 2.92 exponential minus 19. So this will give us 1.17 times 10 to the power minus 19, if I'm not mistaken, joules. Then the second question says, another metal R has a threshold frequency of 7.5 times 10 to the power 14. Will the photo produced in question 10.2 be able to eject electrons from the metal surface of R? Write down yes or no. Let's check. What is the frequency that is produced in 10 point? The frequency that is produced in 10.2 to it's 6.17 times 10 to the power 14 hertz. This is the frequency of light. And what is the cutoff frequency of metal R? It's 7.5 times 10 to the power 14 hertz. You see that the frequency of light is below the cutoff, because cutoff is below, so it means no electrons will be ejected. No electrons will be ejected. Again, we can still compare using the energy of photon and the work function. That's also another way. We can also compare that by comparing the energy. What is the energy of photon? 4.04 times 10 to the power negative 19. So what you can do, you can calculate the work function for metal R by taking H and F naught. H we have, F naught is this one. So we can still compare by doing that. So the answer is no. Why? Because the frequency of light is less than the cutoff frequency. So no electrons will be ejected. One can say the energy of photon is less than the work function. So no electrons will be ejected. And another one can say because the EK maximum is less than 0, it's negative. If the EK maximum is negative, then what does it mean? It means no electrons will be ejected. So there are just many ways to skin a cat, ladies and gentlemen. Remember, practice makes perfect. I think this is the end of this video. Kindly don't forget to like, subscribe, and share with your friends. Thank you very much. Bye-bye.